Welcome to your deep dive. Today we are cracking open the foundational code of chemistry, chemical bonding.
Exactly.
This isn't just, a list of rules. This is how matter itself organizes everything from the salt on your food to, well, to us.
That's right. And our mission today is to take all these concepts, everything from, say, orbital overlap to the subtle forces that dictate boiling points, and just synthesize it all.
Build a mental map.
Build a mental map, yeah. One that lets you connect an atom's arrangement directly to what a substance actually does, its properties.
Okay, so we've broken this down into 4 main areas. We'll kick off with the heavy hitters, the strong primary bonds. Then we'll zoom in on molecular geometry, why things have the shapes they do.
And the quantum theory behind that.
Right. And finally, we'll get to the forces between the molecules, which are surprisingly powerful.
Right.
So let's jump in. The biggest energy transactions in chemistry.
So every atom is basically striving for stability.
Right.
And that usually means getting a full outer shell of electrons, the famous electron octet.
The magic number 8.
The magic number. And this quest, this drive, is what's behind all 3 types of primary chemical bonds. And these are they're extremely strong. It takes a massive amount of energy to break them.
Okay, so first up is ionic bonding.
Yeah.
This is a complete transfer of electrons.
Complete transfer. It's not sharing, it's giving and taking. Typically, you see this between a metal and a non-metal.
Okay.
The mechanism is pretty straightforward. Metal atoms, they lose their outer electrons, become positive cations,
Like sodium.
like sodium losing 1 electron to look like neon. And then non-metal atoms gain those electrons to become negative anions, like chlorine grabbing 1 to look like argon.
And the bond itself is just the attraction between that positive and negative charge.
That's it. It's a powerful electrostatic attraction, and it locks them into a very rigid, repeating structure we call an ionic crystal lattice.
And to visualize this, we use dot and cross diagrams.
Right.
The rules here are pretty simple. You only draw the outer electron shells.
Mm-hmm.
You use dots for one atom's electrons and crosses for the other to show where they came from.
And crucially, you put the final ion in square brackets with the charge written in the top right corner.
Can't forget the charge.
Never. Let's run through a couple. So sodium chloride, NaCl, is the classic. It's a 1-to-1 transfer. Sodium gives 1, chlorine takes 1. Simple.
Okay, what about something like magnesium oxide, MgO?
Good one. So magnesium is in group 2. It needs to lose 2 electrons. And oxygen is in group 16. It needs to gain 2.
So the perfect match.
A perfect 2-electron transfer. Both atoms end up with that super stable neon electron configuration.
But what if it's not a perfect match? Like, calcium fluoride, KF2.
Right. This is where you have to think about the numbers. Calcium needs to lose 2 electrons, but fluorine only wants 1.
So you need 2 fluorines.
You need 2 separate fluorine atoms. The 1 calcium atom transfers 1 electron to the first fluorine and the second electron to the other fluorine. You end up with 1 K2 plus ion and 2 F minus ions.
It's all about balancing the books. Okay, so that's ionic. Second strong one is metallic bonding.
Right, and this is a totally different model. Here you have positive metal ions packed together in a lattice.
Okay, similar so far.
But they're held together by a shared flowing sea of what we call delocalized electrons.
Delocalized, so they don't belong to any single atom anymore.
Exactly. They're mobile. They move throughout the entire structure, and that's the key.
That mobile sea of electrons has to be why metals have their properties, like conductivity.
Absolutely. To conduct electricity, you need mobile charged particles. In a metal, those particles are the electrons. It also explains their high melting points because that attraction between the positive ions and the electron sea is very, very strong.
Okay, so we've had giving electrons and we've had pooling electrons. What's the third one?
The third is covalent bonding. This is the one you see mostly between nonmetals, and it's all about sharing electrons to get to that stable octet.
So the shared electrons are the bond pairs.
Correct. And any outer shell electrons not involved are called lone pairs.
And you can share one pair. A single bond.
Like in hydrogen?
Or 2 pairs.
A double bond.
Like in oxygen. O double bond O. Or even 3 pairs, a triple bond.
Like in nitrogen gas.
Exactly. And triple bond N.
And there's a really important takeaway here about strength, right? More bonds means stronger.
Yeah, absolutely.
Yeah.
A double bond is shorter and has a higher bond energy. That's the energy you need to break it than a single bond does.
Which explains something like nitrogen gas, N2.
It explains it perfectly.
That triple bond has a massive bond energy, almost 1,000 kilojoules per mole.
Which is why nitrogen gas, the air we're breathing, is so incredibly unreactive. It just takes too much energy to rip those two atoms apart.
But that octet rule, that goal of 8 electrons, it's not always followed, is it?
Not at all. And this, for me, is where the chemistry gets really interesting.
Right.
You get atoms that are electron deficient.
Okay, so less than 8.
Way less. A classic example is boron in boron trifluoride, BF3. The central boron atom only has 6 outer electrons, and it's stable like that. And you can also go the other way. You can have more than 8.
You can. It's called the expanded octet. You see it in elements from period 3 onwards, like sulfur, phosphorus, chlorine.
Why them specifically?
Because they have emptied orbitals. They can use those extra available orbitals to accommodate more than 8 electrons.
So an example would be?
Sulfur hexafluoride, SF6.
Okay.
The sulfur in the middle is bonded to 6 fluorines. That's 12 electrons around the central sulfur atom. Or phosphorus pentachloride, PCl5, which has 10. Access to those orbitals just opens up a whole new world of geometry.
And there's one more special type of covalent bond we need to cover, the coordinate bond.
Also called a dative covalent bond. Yes, it's still sharing electrons.
But
instead of each atom bringing 1 electron to the party, one atom provides both electrons for the shared pair.
so you need a donor and an acceptor.
Precisely. You need one atom with a lone pair of electrons it's willing to donate, and the other atom needs to have an empty orbital, making it electron deficient.
The textbook example here is the ammonium ion.
Right, NH4+. You start with ammonia, NH3, which has a lone pair on the nitrogen.
And it bumps into a hydrogen ion, H+, which has no electrons at all.
It's just a bare proton. So the nitrogen just donates its whole lone pair to form a new bond with that hydrogen ion. That's your dative bond.
There was a more complex one in the sources, too, with aluminum chloride.
Yes, the dimerization of LCl3. So a single LCl3 molecule is electron deficient.
Like the boron one.
Exactly. So what happens is 2 of these molecules team up. A chlorine atom from one molecule uses one of its lone pairs to form a coordinate bond to the aluminum atom on the other molecule.
And the other molecule does the same thing back.
It does the same thing back. You get this bridge structure, L2Cl6, and it's much more stable.
Okay, so that's the how of bonding. Now let's talk about the shape. Because as soon as these bonds form, the molecule has to arrange itself in 3D space.
And that arrangement is dictated by a really elegant idea called VSEPR theory.
Valence shell electron pair repulsion.
That's the one. The core idea is just, it's simple. Electron pairs are all negatively charged, so they repel each other. They will arrange themselves to be as far apart as possible.
To minimize that repulsion.
To minimize repulsion and find the lowest energy state.
But, and this is the crucial part, not all repulsions are equal.
No, not at all. There's a clear hierarchy. The strongest repulsion is between 2 lone pairs.
Lone pair.
And that's stronger than the repulsion between a lone pair and a bonding pair.
And that in turn is stronger than 2 bonding pairs repelling each other.
Exactly. You can think of lone pairs as being bigger, puffier clouds of charge. They take up more space and they bully the bonding pairs.
Let's see that in action. Let's start with a molecule with 4 electron pairs around the center, like methane, CH4.
Perfect example. 4 identical bonding pairs, no lone pairs. The repulsion is equal in all directions.
You get that perfect tetrahedral shape.
With a bond angle of 109.5 degrees. Now let's tweak it. Swap one of those bonds for a lone pair. Now you have ammonia, NH3.
3 bonding pairs, 1 lone pair.
And that lone pair's stronger repulsion shoves the 3 bonding pairs a little closer together.
So the shape changes from tetrahedral to...
Pyramidal. Pyramidal, yeah. And the angle gets squeezed down to 107 degrees.
Okay, let's do one more. Water. H2O.
Right. 2 bonding pairs, 2 lone pairs. Now you have that really strong lone pair repulsion at work.
Pushing the 2 hydrogen bonds even closer together.
Even closer. The shape becomes V-shaped, or nonlinear, and the angle is compressed all the way down to 104.5 degrees.
So that progression, 109.5, 107, 104.5, is the proof.
It's the physical evidence of that repulsion hierarchy.
And this scales up, right? 3 pairs gives you trigonal planar.
120 degrees, like in BF3. 6 pairs gives you octahedral.
Like in SF6 with all 90-degree angles.
Exactly. The principle holds.
So to really understand why these bonds point where they do, we need to go a level deeper into orbital theory.
Right. A covalent bond is really the overlap of atomic orbitals, those S and P orbitals, to form a new shared molecular orbital.
And sometimes these orbitals mix together first, in a process called hybridisation.
Yes. They form new hybrid orbitals, SFT3, SP2, SEC, that are better shaped for bonding. We can then classify the bonds based on how they overlap.
The first type is the sigma bond, the Greek letter sigma.
Right. Sigma bonds are formed from a direct end-on linear overlap of orbitals. The electron density is concentrated right between the two nuclei.
And every single covalent bond is a sigma bond.
Every single bond contains one and only one sigma bond.
So what's the other type?
The other type is the pi bond, Greek letter pi. These are different. They form from the sideways overlap of p orbitals.
Sideways. Okay, so not end-to-end.
Not end-to-end. And because of this, the electron density isn't on the axis between the atoms. It's actually in two lobes, one above the axis and one below it.
So if we look at a double bond, like an ethene, C2H4,
that double bond is made of one sigma bond and one pi bond.
and that pi bond has a huge effect on the molecule.
It's critical. It locks the molecule into a rigid, flat shape. You can't have free rotation around a double bond because you'd have to break that sideways pi overlap.
And a triple bond, like an N2.
That's one sigma bond and two pi bonds, oriented at 90 degrees to each other.
Okay,
Really?
let's shift gears. We've talked about the forces inside molecules. What about the forces between them?
Yes, the intermolecular forces, or collectively, van der Waals forces. These are much weaker than the primary bonds, but they are absolutely critical for determining physical properties like boiling points.
And to understand them, we first need to talk about electronegativity.
The tug of war.
The tug-of-war for electrons within a bond. It's defined as the power of an atom to attract the shared electrons towards itself.
And the trend is pretty clear. It increases as you go across a period on the periodic table, and it increases as you go up a group.
Making fluorine the king.
Fluorine is the most electronegative element with a value of 4.0 on the Pauling scale.
And we can use that scale to predict what kind of bond will form.
We can. A big difference in electronegativity, say 2.0 or more, means one atom pulls so hard that the electron is just transferred. It's an ionic bond.
Like in NaCl.
Exactly. But if the difference is small, say 1.0 or less, the electrons are shared pretty equally. It's a covalent bond.
But what about the middle ground, where the shearing is unequal?
That's where you get a polar bond, or a dipole. The electrons spend more time around the more electronegative atom, giving it a slight negative charge, which we write as delta minus.
And that leaves the other atom with a slight positive charge, delta plus.
Correct. But, and this is a really common mistake,
Go on.
a molecule can have polar bonds but be non-polar overall.
Because of the shape. VSEPR again.
VSEPR again. Take carbon tetrachloride, CCl4. You have 4 polar CCl bonds, but they're arranged in that perfect tetrahedron. They all pull in opposite directions and cancel each other out.
So the molecule as a whole is nonpolar.
Correct. But if you swap one chlorine for a hydrogen, making chloroform CHCl3,
The symmetry is broken.
the symmetry is broken, the dipoles don't cancel, and the whole molecule becomes polar.
Okay, now we can finally talk about the van der Waals forces. Let's start with the weakest one.
That would be the instantaneous dipole-induced dipole forces, or, much easier to say, London dispersion forces.
And these exist between all molecules.
All of them, even nonpolar ones.
Mhm.
Because electrons are always moving, at any given instant, the electron cloud can be lopsided.
Creating a temporary instantaneous dipole.
Exactly. And that temporary dipole will then induce a dipole in the molecule next to it, creating a very weak, very brief attraction.
And they get stronger with more electrons.
More electrons means a bigger, more polarizable cloud, so stronger forces. That's why big molecules have higher boiling points than small ones.
Okay, what's the next step up?
Permanent dipole forces. These only happen between polar molecules.
It's just the attraction between the delta plus end of one molecule and the delta minus end of its neighbor.
That's all it is. It's stronger than a dispersion force because the dipoles are permanent, not fleeting.
And that brings us to the king of the intermolecular forces,
Hydrogen bonding.
which is really just a special super strong case of a permanent dipole force.
A very special case with very strict requirements.
Okay, what are they?
First, you need a hydrogen atom that is covalently bonded to one of only 3 elements: fluorine, oxygen, or nitrogen.
The 3 most electronegative.
Right. And second, you need a neighboring molecule that has a lone pair of electrons on an F, O, or N atom.
And these are strong, for an intermolecular force anyway.
They're still much weaker than a proper covalent bond, but they are significantly stronger than any other van der Waals force, and their impact is just immense.
And the number one example is always the anomalous properties of water.
It has to be. Water forms this huge, extensive network of hydrogen bonds. On average, each water molecule is hydrogen bonded to 2 others.
And breaking all those bonds takes a lot of energy.
A huge amount of energy, which is why water has such a ridiculously high boiling point for such a small molecule. Without H-bonds, water would be a gas at room temperature. Life wouldn't exist.
But the weirdest property is density. The fact that ice is less dense than liquid water.
It's incredible. When water freezes, those hydrogen bonds don't just pull things together randomly. They force the molecules into a very ordered, open 3D lattice.
Open lattice, so there's empty space.
There's empty space, which means the molecules are held slightly further apart, on average, than they are in the jumbled, chaotic liquid state.
So the solid is less dense than the liquid. Ice floats.
Ice floats, a simple fact with planetary consequences. It means lakes and oceans freeze from the top down, insulating the water below.
So to pull this all together, structure dictates property.
It's the central theme. Ionic compounds and metals form these giant structures. They have high melting points.
Simple covalent molecules have weak intermolecular forces, so they have low melting and boiling points.
Right. And conductivity always comes down to mobile charged particles.
Metals have mobile electrons, so they always conduct.
Ionic compounds only conduct when they're molten or dissolved because that's when their ions are free to move.
And covalent molecules
never conduct. No mobile charged particles.
So we have covered a massive amount of ground here. We've linked the electrostatic pull in a salt crystal to VSEPR to orbital overlap, all the way to hydrogen bonding in water.
You really have the complete map now, from the quantum to the macroscopic.
And remember, every property you can observe, a substance's melting point, its solubility, its conductivity, it all traces back to the bonding and the geometry we've discussed.
And we'll leave you with this final thought to chew on. Consider how that very specific geometric requirement of hydrogen bonds didn't just make ice float. It fundamentally shaped our planet's entire climate system, all because of the angle and strength of an intermolecular force.
We wish you the best in your studies. Thank you for joining us on this deep dive.